Let's go ahead and sketch this piecewise function and then find domain and range. And oops. So I'm going to let our function be. I'm going to keep it pretty simple for now, and then we'll do more complicated trig stuff. But for now, I'm just going to ask us to graph 3 cosine of x for x less than or equal to pi. And we're going to graph x minus pi squared for x greater than pi. And I will again give you a couple minutes to try to sketch that on your own. I don't want to leave people staring at a blank paper for too long. So how many people would like a little more time? Happy to give it. Okay, so let's do like 1 more minute. And if you have some sort of web-enabled device in front of you, you could always pull up Desmos and see if you can see how you did with your graph. Based on what I was seeing walking around the room, I'm going to pause for a second and come back to this, but I want to make sure that we talk about the like base or parent graphs for cosine and sine really quick. And we'll come back to what that 3 is going to do to it. So quick trig parent graphs. So 2 of our trig friends, sine and cosine. Y is equal to sine of x. This graph starts at 0 and sine always heads towards its highest value first, like the regular sine graph. And we think about sine, usually we think about it in the first quadrant. It keeps going in the other, in the first and fourth quadrants, it keeps going in the other direction too. But sine of 0 is 0. Sine of 2 pi is also 0. Sine of pi is also 0. And then at pi over 2 and 3 pi over 2, sine gets all the way down here to -1 or all the way up here to +1. Cosine is actually just this sine graph shifted over. Pi over 2, and for those of you who might take physics sometime in the future, you might talk about that a little bit in physics when we talk about phase shifting, but we don't need to know the physics right now. Our cosine graph, I'm gonna like run out of space on this page, but I'm gonna do my best. Starts up here at 1, dives down to -1, and comes back up to 1. And just like sine, we say it finishes one period at 2 pi. So it's at that lowest point at pi, and then it crosses at pi over 2 and 3 pi over 2. And just like the sine graph, we usually think about it heading in the forward direction, sort of towards those positive values. But technically, there is nothing that stops either of these graphs, and they keep going forever in both directions. So here it would hit again at -pi. And I suppose I should actually write in what this function was. That my pen is dying. That's probably why it was sitting over there. Y equals cosine of x. At some point in time, if you haven't already, you will be expected to know certain values of sine and cosine. You'll be expected to know kind of values for those nice angles. So in degrees, we're thinking 30 degrees, 45, 60 degrees, 90 degrees, and then those values in each of the 4 quadrants. Or if we're thinking in radians, we're thinking about pi over 6, pi over 4, pi over 3, pi over 2, and then all of those values in the quadrants. Personally, because you're going to have to know what the graphs look like, and also you're going to have to know the values, I like to use the graph to know the values at like 0, pi over 2, pi, 3 pi over 2, 2 pi. If you're a unit circle person, that's fine too, right? But if you haven't found something that works for you to memorize yet, the time has come. You will be expected to get all those things memorized. Repetition tends to help, so I will keep throwing some trig our way. I'm going to flip back to our problem now. So this is our base graph for cosine, or our parent graph. We can talk tangent. So our base parent graph for tangent of x, because tangent of x can be written as sine of x over cosine x, our tangent graph is kind of like a rational function in that it has vertical asymptotes when the denominator is trying to be 0. Since the denominator in our tangent graph is really coming from cosine, that means the denominator is trying to be 0 when I'm at pi over 2, or 3 pi over 2, or negative pi over 2, or negative 3 pi over 2. So that tangent graph looks a lot like it is not a cubic, but shape-wise, to kind of remember what it looks like, it looks kind of like a cubic that is squeezed between the vertical asymptotes. So pi over 2, negative pi over 2, those are going to be vertical asymptotes for that tangent graph. And then it's going to repeat, just like the sine and cosine graphs, but it's going to repeat squeezed between another set of vertical asymptotes. in terms of the tangent graph, or like in general, if I take the graph and I multiply it by a number, that's either stretching it or kind of compressing it. If I think about what it does to like a parabola. For the tangent graph, there isn't really something nice that you can draw if it's been stretched or compressed this way, because it kind of keeps its shape. It just goes up faster or slower. But for the sine and cosine graphs, when we stretch them out, it's going to change where those kind of top and bottom points for the curves are. Can I flip back to the one I gave us? Okay. So if I take that regular cosine graph, the 3 out in front means that it's actually going to hit a max height of 3 and a max low of -3. That's where it would be stuck between. So I know that at 0, cosine of 0 is 1. So I'd have like 1 times 3, or that y-intercept would be up here at 3. And since it's a cosine graph, that's my high point. And I know I'm looking at the left-hand side of pi, so it would do something like that over there and keep going. But I haven't quite gotten to pi yet. So in terms of that cosine graph, it gets down to the bottom at pi. And that would be -3. Because that side has the or equal to on it, I'm going to give it a filled in circle. So that's our left-hand side. On the right-hand side, we're looking at a parabola. And even though I gave us kind of an maybe ugly thing to put in there, if this just said y equals x minus 3 squared, what does that -3 do to the parabola? What direction does it shift it? Left, right, up, down. And this would shift it. This would shift my vertex 3 to the right. So this is shifting it pi to the right. So my vertex is going to be here at pi. And then I'm just going to draw that parabola in. Just for fun, if we wanted to practice that on Desmos. I haven't done this in a while, so let's see if I can make this work. So we're going to have 3 cosine x. And does anyone know how Desmos likes pi? Can I just type pi? I can. So I typed a lowercase pi to get that pi out of Desmos. And then our other one here, we need y is equal to x minus, again, lowercase pi, and it'll just automatically switch that for us.
And I think there's that little keyboard button on the bottom.
Oh, I have like never noticed that. That's cool. Need to get out of my exponent. And this was for x greater than. Now I'm going to try it. Cool keyboard button. And pi. Sweet. I typed a lowercase pi to get pi. But thank you. I have now learned that there is a little keyboard button in the corner, and pi is also hiding in that keyboard button. Thanks. I will say Desmos is not great about showing the filled in circle versus open circle. I have noticed that over time. So that's definitely something that you're going to have to know whether to put the filled in circle or the open circle. All right, move off of our Desmos section. Go back to my notes. question. Yes.
Cosine of pi is 8. Or sorry, when you plug in like x equals pi, you get this cosine of pi and then times 3.
Yeah. So at x equals pi, we're looking at 3 times cosine of pi. And cosine of pi is -1. And there are a couple of different ways that we can think about cosine of pi being -1. So if you're a unit circle person, then we can get to cosine of pi being equal to, I don't know if this was your question. Hopefully, I'm hoping it is. So if you're a unit circle person, then starting over here at 0 radians, over here I'm at pi radians. And that coordinate right there has an x value of -1 and a y value of 0. And so that -1 corresponds to the cosine of pi. And that 0 corresponds to sine of pi. If you are not a unit circle person, then the other option that I would offer up is knowing what the parent graphs look like. So the parent graph for cosine of x has a y value of -1 at pi.
So you get -1 times -1, which is as the y value.
Yep, that's what I got. So this is the point pi comma -3. This part is from the parabola where plugging in pi gives me 0. So maybe you were looking at this one, but that's my parabola side. On my cosine side, I did get a y value of -3. Oh yeah. That better?
And then to find the y-intercept.
So the y-intercepts, no matter what the graph is, no matter what my function is, my y-intercept is always where x equals 0. Every single time. So to get that y-intercept of +3, I would be looking at 3 times cosine of 0. And cosine of 0, again, if you're a unit circle person, over here at 0 degrees, that x value is 1, which corresponds to cosine of 0. And that 0 corresponds to sine of 0. So this would be 3 times +1 for that x-intercept. Yeah. Dun, dun, dun. We still haven't found the domain and range. I want to give everyone a minute, now that we've got a graph, to write the domain and range. Give it a shot for yourself if you didn't get a chance to try it before. So in terms of domain and range, with sine and cosine, I don't have any asymptotes happening because they're both just continuing forever in both directions. So I know that cosine piece from a domain perspective, it's good all the way up to pi, My parabolas have no domain issues. That domain's negative infinity to infinity. So I can say all real numbers or negative infinity to positive infinity. In terms of the range, I'm thinking about lowest y value on the graph to highest y value on the graph. The lowest value we ever hit for y is -3. But the highest y value is going to be, that parabola is going to keep going forever. And I can actually get to -3. So that's going to be a square bracket, and I'm going from -3 to positive infinity for the range. Questions before I move on a little bit? I am going to throw a really weird piecewise graph at us. Just, I'm not going to make us graph it. Just if I gave you this graph, I wanted to talk about what the range, domain range kind of issues would be. So find the domain and range. And I'm going to sketch the graph for us. And I'm making it intentionally really weird. Sure. So my function is going to look like, I'm not going to get like super crazy, but let me just go 1 over x minus 2. Nope, x plus 2 for x less than 0 and that's not going to do what I wanted. Sorry. We're just going to make it 1 over x. I'm not going to try to make it fancy. Okay. 1 over x for x less than 0 and x minus 1 squared plus 3 for x greater than 0. And I'm going to sketch the graph for us. Oops. So first of all, thinking about domain, 0 has to be left out of my domain because we're not taking either of these functions at 0. So my domain would have to look like negative infinity to 0, punch a little hole, go to positive infinity. Now my range has a hole punched in it as well. So if I think about lowest values to highest values on the graph, even though I can go down as far as I want and up as far as I want on the graph, there is this window in here between 0 and 1 that I can't get to on the curve. So my range here would have to look like negative infinity to 0. And then from, oh, sorry, I meant from 0 to 3, 3 to positive infinity. Neither of the functions can get me to any of the y values between 0 and 3. Questions before we go on to maybe more trig stuff? I know people are still catching up in notes. Yeah. Yeah, so. Great question. So the parentheses, I'm always going to have parentheses for infinity, whether that's positive infinity or negative infinity. That's never a value that I can actually get to where we're going to have a bracket. I'm also going to be thinking about parentheses in general when we have asymptotes, whether those are vertical asymptotes or horizontal asymptotes. I kind of want to be thinking parentheses usually there. Brackets mean that I can actually get to that point. So, by the way, if I took this graph and I modified our function just slightly, so instead my f of x looked like 1 over x for x less than 0, and then x minus 1 squared plus 3 for x greater than or equal to 0. That change would be enough that my domain would now be negative infinity to positive infinity. When x is actually equal to 0, I'm not at this vertical asymptote from this function. I have a place to plug it in. And if there's a place where I can actually plug it in and nothing bad happens, then that is included in my domain. Doing that didn't change my range at all. The range would still be negative infinity to 0 and then 3 to infinity. In general, with parabolas, we can actually get to the value at the vertex. In general, with trig, with sines and cosines, I can actually get to those highest and lowest values. But if we're thinking about logs or exponential graphs where we have those asymptotes, those are values that I can't actually get to. So those are values that end up with parentheses. Just kind of generally. How are we feeling? Do we want a little 5-minute break? Push through? Maybe I'll end a little early. Yeah? Okay, that'll be my trade-off. We'll end it. I'll try to wrap up a little early today. So options for where we go next. We can do more trig review, like thinking about angles in radians, finding values for sine, cosine, tangent at our special angles, talking special triangle stuff, so we can like do some general trig review. There were also homework questions specific to some of the manipulating graph stuff, and then those word problems that involve formulas. I could go there, or we can kind of get a preview of where we're headed with exponential growth. Anyone have strong opinions? Trig review? Okay, let's do a little more trig review. Fair or not, trig is a prerequisite for calculus. It is assumed that you've had trig before. If you really have not had trig before, it doesn't mean that you can't survive calculus. It just might mean that there's a little bit more for you to memorize. Okay. But let's talk about, in addition to the graphs of trig functions, other things that are sort of expected that you are going to know about trig. If I gave us a lovely right triangle and I labeled these sides y, x, and r, and I put a theta down here in this corner, it is expected that as ratios of the sides of the triangle, that you would know what sine, cosine, and tangent look like, and then all of their reciprocal friends. A lot of people have this memorized or remember it using the phrase SOHCAHTOA. It's just a memorization trick. I like to write it out as so TOA. And the reason that I write it this way is because it helps me remember who's on top, who's on the bottom for each of those. It is not the only way to memorize this stuff. So when I think about sine of theta, that's defined as the ratio of the sides of this triangle, where I've got the side opposite to the angle, and that's what the O stands for, divided by the hypotenuse. Now, the reason that I've written this as y over r is strategically to help me think about, if you're a unit circle person, to connect back to sine of theta goes with the y value on the unit circle. And if that doesn't make sense to you, don't worry about it. Cosine is the adjacent side over the hypotenuse. So in terms of my triangle here, that's the side, it's the leg that is adjacent to or touching the angle still. So I'm going to have an x over r, and tangent is y over x. They're reciprocal functions, meaning the hypotenuse over the opposite side, or r over y, r over x, x over y. Their names are cotangent, cosecant, and secant. Oops, I lost my theta on my cosecant. Honestly, in calculus, we use these three the most, but secant shows up because it's got relations to tangent that we will talk about when we get to derivatives. So secant tends to show up too. Cosecant and cotangent don't show up as much. And when they do, I usually switch them around to be sines, cosines, and tangents anyway. I don't consider this next bit to be trig identities. I consider this to be part of what you should memorize in terms of these relationships. So cotangent. Now let me start with tangent. I already wrote it up there, that tangent is sine over cosine. So cotangent is cosine over sine. It's also 1 over tangent. And it becomes important sometimes that we're able to flip things around in different ways, because we have information about one of these things, but maybe not the others. In terms of cosecant, that's the same as 1 over sine of x, which also lets me know that we're going to have domain problems anywhere that sine is trying to be equal to 0. Secant is 1 over cosine of x, which means we're going to have domain problems anytime cosine is trying to be 0. There is one trig identity that you absolutely must memorize, and we will use a lot. My guess is some of you know it. Can anyone tell me the value of sine squared theta plus cosine squared theta? Oh, I got a hand. Yes.
1.
Perfect. If that didn't just roll off the top of your tongue, we should get that memorized. This thing we use all the time. I would say the double angle and half angle formulas are also trig identities that are pretty helpful, that come up quite a bit in calculus. I'm gonna pause on those until they do show up for us, and then we'll talk about them. Instead, I want to talk about angles for which we have our special triangles and the values that we're supposed to memorize for sine, cosine, tangent for those special angles. flipping the page unless I've got requests to pause here for a second. Okay. More trig stuff. Let's talk radians for a second. You can blame the physicists for radians. So a few hundred years ago, physicists invented calculus. When they invented calculus, and that's like, you can talk to physics professors about this if you want, but mathematicians might disagree, but I'm going to, physicists invented calculus because they needed it to explain the physics that they were observing. When physicists invented calculus, they didn't want to have these units of degrees or things that were happening that depended on how big the object was. So if you think about like a cylinder rolling down a ramp or something, they wanted a way to talk about the physics of it, regardless of the size of the object. So instead of working in degrees, which also is fairly arbitrary, so 360 degrees, there's some disagreement about historically how we ended up at 360, but it's a pretty arbitrary unit to have split a circle up into. There are lots of great reasons for it, but physicists wanted something that was independent of the size of the object and felt less arbitrary. So they split the circle up based on the distance around the circle, which is 2 pi times the radius of the circle. So they named the thing 2 pi radians. So then regardless of the size of the circle, it's always 2 pi radians to get around it. It's how we ended up at radians. We don't need to know the history of that. We just need to know that if I start at 0 degrees, that's also 0 radians. Going all the way around the circle was 360 degrees, but that's 2 pi radians. Halfway around the circle, that's 180 degrees or pi radians. A quarter of the way around the circle, that's pi over 2 or 90 degrees. This is 3 pi over 2. Now, why am we working in radians? Because physicists invented calculus. Therefore, calculus only works in radians. You actually have to work really hard to do calculus in degrees, and you have to do all this unit conversion stuff. But if we just do calculus in radians, we're good to go. So because of that, it's important that we've got our special triangle angles memorized, not just in degrees, but also in radians. That's a square. How big should the sides of my square be? It doesn't actually matter to me. Cool, how about 1? We'll keep it simple, keep our numbers small. So if the sides of my square are 1, and because it's a square, all those interior angles are 90 degrees or pi over 2. When I cut this in half, now that angle is going to be pi over 4. And I can use the Pythagorean theorem to come up with what the hypotenuse is. Pythagorean theorem says 1 squared plus my other 1 squared has to be equal to the length of that hypotenuse, not hypothesis, the length of my hypotenuse squared. So 2 is going to have to be equal to c squared, which means this length is the square root of 2. Using that picture, I can now say, okay, so cosine of pi over 4 is equal to 1 over the square root of 2. If that bothers you in any way, or that is not how you memorized it, it's also important to know that in a world before calculators, when people were using slide rules and log tables, it is not easy to divide by a decimal value on a slide rule. It is easy to divide by a whole number. So in a world before calculators, it was important to rationalize denominators. It's not anymore, but somehow we have this mathematical holdup about it. If I multiply the top and the bottom of this by the square root of 2, I end up with the square root of 2 over 2. However you want to think about this is fine. I like the 1 over square root of 2 because I can see it in the picture. And the square root of 2 over 2 for me feels like something arbitrary that we've memorized. By the way, for the same picture, sine of pi over 4 is also 1 over the square root of 2. And tangent of pi over 4 is equal to 1. Or 1 over 1. Now my guess is pi over 4 feels friendly, and maybe a bunch of you already had that one memorized, and the one that trips people up is pi over 3 or pi over 6 and kind of remembering which is which. Well, here's the good news. Just remember one fact about pi over 3 and pi over 6, and you'll know which is which. So you just need one fact. If you know that it goes with a 2 and a square root of 3, just solidify one thing in your brain and you'll be able to figure the rest of it out. But I'm going to draw a picture. And that one is coming from an equilateral triangle. I'm going to choose a side length of 2 this time because it's in my best interest math-wise. So this was an equilateral triangle, meaning all of the interior angles were 60 degrees, or pi over 3. And if I cut this triangle in half, then it also means I've cut the angle in half. And if I cut it in half, then this bottom length was 2, but I cut it in half, so now it's 1. And if I use the Pythagorean theorem, I'm going to get a height of square root of 3 for that side. So if I'm looking at cosine of pi over 3 and sine of pi over 3, cosine of pi over 3, that's the adjacent side over the hypotenuse, or 1/2. Sine is the opposite side, so square root of 3 over 2. And if I look at cosine of pi over 6 and sine of pi over 6, it's basically the same triangle if I just turn my head. So cosine of pi over 6 means I'm now looking at that adjacent side of the square root of 3, the opposite side being 2. For sine, that opposite, I meant hypotenuse being 2, opposite side being 1, hypotenuse still being 2. Well, if you just memorize one of these, my guess is you can figure the rest of them out. So for example, if you were to just know this, that cosine of pi over 3 is equal to 1/2. Then if I started from cosine of pi over 3 is equal to 1/2, I could really quickly draw a triangle, even if it's not pretty, and go pi over 3, if cosine is equal to 1/2, that's a 1 and a 2. And then I would know what the missing side was, and I would know what the missing angle was really quick. So my recommendation, if you haven't found something that works to memorize these yet, just memorize exactly one of them. And if you memorize exactly one of them, you can always recreate the rest. Yeah.
Why did you get like the middle line?
Yeah. So if we had that side was 2 and that side was 1, and I wasn't sure what that side was, then Pythagorean theorem is going to look like 1 squared plus that missing side squared is equal to 2 squared. So 1 plus something squared is equal to 4, which means my something squared must be equal to 3, and b is the square root of 3. Should we talk about unit circle and stuffing quadrants? Or we're like tapped out on trig for the day? How about we revisit that another time, because I want to make sure that I've got time to address, to visit a couple of homework problems that people had asked about. The first homework question someone asked about in the chat. I was helping some folks with in office hours on Friday, and it took me a minute to like figure out what was happening in my head. So I wanted to make sure to share it with everyone else. So the question says we're going to start with y equals e to the x, but reflect across y equal, no, we're reflecting. Oh, I am going to do this one, even though it asked about x equals 1. I'm going to reflect across a y value first. So if I wanted to reflect this across y is equal to 1, and then we had to write the equation, the new equation for the graph. Now, I know that there are ways to do this without sketching a graph, but that's not how my brain works. I need to see the picture. I will also say you could just kind of play around with it in Desmos till you get to the right picture. But this says I'm starting with a graph of e to the x. And then we're drawing in this line at y equals 1, which happens to be where that crosses. And I'm reflecting it. So it's kind of doing this. So this one has flipped over, meaning this is a negative e to the x graph, but the asymptote didn't shift by 1, it actually shifts by 2. Because the distance from my asymptote to what I was reflecting around was 1, which means when we do that reflection and spin it, this new asymptote is like another 1 away, meaning it's been shifted up a total of 2. And I know that's a little weird. Now, I misread the question in the chat, so I'm going to do the actual question that was in the chat, which was to take that y equals e to the x graph and instead reflect across x equals 1. Starting with my e to the x graph, coming over here to x equals 1 now. And this is not an asymptote, it's just my magic reflecting line. So I'm reflecting. So it's now looking like this. So first of all, making that reflection means I'm looking at some sort of y equals e to the negative x. But also we need to be shifted over. So the way that I'm going to think about that, how far we're shifted over, is kind of the same way that I thought about the other one being shifted. So if I think about my anchor point as being the e to the 0 being equal to 1, and if I kind of hold that as my anchor point, then that same y value has actually shifted over to here. It's shifted over 2, not 1. So I've reflected it, but also shifted over 2. Meaning that when I plug in x equals 2, I need to get e to the 0. It's not the only way to write it, but I think it'll do it. When I plug in 2 for x, I now get e to the 0, which is what we were looking for. And that minus sign in front of the x is going to make sure that we've done the reflection part. And you could also write this as e to the 2 minus x. You could also write that as e to the negative x minus 2. And those 3 options just sort of embody whether you wanted to move it first and then spin it, or spin it first and then move it. Okay, I said I would end a little early. It is 10:10. I'm going to talk through that geometry problem for anyone that wants to hang out. So, oh, yep. Leave that for a second. Heck yeah.
Why is negative x plus 2 for the power? I know I heard you explain it, it's just not sticking.
No, it's all good. It's all good. So I think about it graphically, and I just think about where do I need that point to move? So because I need this point to move over there,
Because that point is e to the
0, I just need to know what do I have to stick there so that when I plug in 2, I get 0. That's the way I look at it.
Okay.
You could also think about it as I had to take the graph and shift it over 2, right? So like just e to the negative x would look like this. And so I need to move that e to the x graph over 2 to the right, the e to the negative x. So this would be the version that looks more like that, right? Then I'm going to do a negative, so it's decreasing, but I got to shift it 2 to the right.
Okay.
Okay. So there was a question, and I did see that Weber problem. Various forms, various numbers, but you are told that you have a rectangle. And I'm just going to call that the width and that the length. And I don't remember exactly what it said, but something like the area is equal to, I'm going to pick a number, I'm going to choose 12. The area is equal to 12. Find the perimeter as a function of the length.
Oh, one of the sides, it said. Okay.
So if it's a rectangle, I don't have any reason to believe that these 2 values are equal. And I don't have enough information to know what those 2 values are. But the thing it has asked us to find is something for the perimeter. So I would just start by writing what the perimeter. I'm like having trouble writing today. I'm gonna call it P for perimeter, and y'all know what I mean. So here's this is one of the web word problems. Yeah. So though we don't need calculus to do it. So our perimeter for this shape is 2 times the width plus 2 times the length. And all this problem is saying is eliminate one of the 2 variables so that we're only rating it as a function of the length not the width and the length. So we're going to come off to the side and say, oh, I hope they gave us more information, and they did. They told us the area was 12. Well, if my area is 12, and I know the area is equal to the length times the width, and that's equal to 12, then I can eliminate W by solving this other equation for W. And then I can take that to stick in, so that our perimeter as a function of only the length becomes 2 times 12 over L plus 2 times L. And WebWork would take it like that. This problem in particular said it's case sensitive, make sure you use a capital L.